The deepest point in our ocean is almost 11,000 meters down, and that is a staggering distance, difficult for the human mind to truly grasp. Imagine the tallest mountain you have ever seen, a giant of rock and ice piercing the clouds. Now picture that same mountain, but turned completely upside down, its peak pointing not to the sky but down into the dark, silent water. The very tip of this inverted mountain would still not touch the bottom. That deepest place, a part of the Mariana Trench, is called the Challenger Deep. It is a world of crushing pressure, profound cold, and an eternal, lightless night. Before we continue, welcome back to GeoVenture. Please like and subscribe for more. Thanks. The Mariana Trench is a crescent-shaped scar on the floor of the western Pacific Ocean. It stretches for over 2,500 kilometers, a vast and imposing feature of our planet's geology. This trench was formed by a process called subduction, where one massive tectonic plate, the Pacific Plate, is slowly being forced underneath the smaller Mariana Plate. This colossal, slow-motion collision has created the deepest chasm known to us. Above, the ocean's surface appears calm and uniform, giving no hint of the dramatic topography that lies miles below. At the southern end of this trench lies its most famous and profound point, the Challenger Deep. Reaching a depth of nearly 11,000 meters, it represents the ultimate frontier of oceanic exploration. Very few humans have ever made the journey to this spot. The first to do so were Jacques Piccard and Don Walsh in 1960, descending in a bathyscaphe named Trieste, designed to withstand extraordinary pressures. While the Mariana Trench holds the title for the deepest, our planet's oceans hide many other stupendous trenches. Just northeast of New Zealand lies the Tonga Trench, the second deepest. It plunges to over 10,800 meters, nearly as deep as the Challenger Deep. Like the Mariana, it's a subduction zone, a hotspot of seismic activity. The same immense forces that make earthquakes have carved this abyss into the seafloor, creating a unique, extreme habitat. The water in the Tonga Trench is not empty. It's a world teeming with life very different from sunlit shallows. Nearby, the Kermadec Trench cuts a deep scar into the Pacific. It's notable for hydrothermal vent systems, underwater geysers where superheated, mineral-rich water erupts. Around these vents, without sunlight, entire ecosystems thrive. Tube worms with bright red plumes, dense beds of mussels and clams, pale, ghostly crabs clustered near vents. The Atlantic's deepest point is the Puerto Rico Trench. Just north of Puerto Rico, it reaches over 8,300 meters. It's geologically complex, sitting at the Caribbean and North American plate boundary. Each trench is its own world, a natural laboratory for studying geology, chemistry, and the very limits of life. The single greatest challenge to life and exploration in the deep sea is the immense pressure. As one descends, the weight of all the water above exerts a powerful force. For every 10 meters you go down, the pressure increases by 1 atmosphere, the same pressure we feel at sea level. At the bottom of the Challenger Deep, at nearly 11,000 meters, the pressure is more than 1,100 times that at the surface. This is a force equivalent to having 50 jumbo jets stacked on top of a person. It is a pressure that would instantly crush any unprotected organism or machine. For this reason, vehicles built for the deep must be engineering marvels. Manned submersibles are typically spherical, the strongest shape for resisting pressure from all sides. Their hulls are made of incredibly thick steel or titanium alloys. Every window, every seal, and every wire must be perfectly designed and tested to withstand this relentless force. Robotic vehicles face the same challenge. Their electronic components must be housed in pressure-resistant casings filled with oil to equalize the force, ensuring they can function in this extreme environment without being imploded. Section 5. Life in the Abyss. Thriving against the odds. In the complete darkness of the deep sea, many creatures have evolved the ability to produce their own light. Bioluminescence transforms the abyss into a silent, slow-motion fireworks display. Tiny shrimp release glowing clouds to startle predators. The anglerfish dangles a luminous lure in front of its mouth to attract prey. This living light is used for communication, for camouflage, for finding a mate. This living light is used for hunting. The colors are often blues. The colors are often greens. They create dazzling patterns in the black. Food in the deep sea is incredibly scarce. With no sunlight, ecosystems rely on a gentle rain of organic matter from above, marine snow, dead plankton, fecal pellets, remnants of larger animals, and other debris. It is the foundation of the deep sea food web. Scavengers like the hagfish find these meals. The giant amphipod is another expert scavenger. A whale carcass sinking to the bottom becomes a long-lasting feast. Deep-sea creatures are shaped by extreme conditions. They show life's tenacity and creative adaptation. Even in the most remote and deepest parts of our planet, we are now finding unmistakable evidence of our own presence. When explorers journey to the bottom of the Mariana Trench, they find not only wondrous new species but also plastic bags and candy wrappers. This is a sobering and profound discovery. It shows that our waste, when discarded carelessly, does not simply disappear. Ocean currents can transport light materials like plastic across vast distances. Eventually, they can sink into the abyss where they will remain for centuries or even millennia in the cold, dark, and slow-moving environment. This pollution is more than just an aesthetic problem. It poses a real threat to the delicate life of the deep. Animals can mistake small pieces of plastic for food, leading to internal injury and starvation. As these plastics slowly break down into microplastics, they can be ingested by smaller organisms at the very base of the food web, introducing harmful chemicals into the ecosystem. Our impact is also felt through other activities. Bottom trawling can devastate ancient deep-sea coral gardens and sponge beds. The prospect of deep-sea mining threatens unique ecosystems found nowhere else on Earth. The deep sea keeps a quiet record of our actions. The presence of a simple plastic bag at 11,000 meters is a powerful reminder that there is no away when we throw something away. It underscores our responsibility as stewards, from the highest mountains to the deepest trenches. The quest for depth does not end at the ocean's edge. Some of the world's lakes are so vast and deep that they are like freshwater seas. The most profound of these is Lake Baikal, located in the remote wilderness of Siberia, Russia. It is the deepest lake on Earth, plunging to a staggering 1,642 meters. It is also the world's oldest lake, at around 25 million years old. It holds about 1/5 of all the world's unfrozen fresh water. Its water is exceptionally clear. Its long isolation has allowed thousands of unique species to evolve. One famous inhabitant is the Nerpa, the world's only exclusively freshwater seal. The lake's depths are cold, dark, and oxygen-rich, supporting a unique ecosystem. Studying Lake Baikal is like looking into an ancient evolutionary past and a barometer for regional environmental health. In Africa, Lake Tanganyika is the second deepest, reaching 1,470 meters, ancient, and home to hundreds of unique cichlid species. Its deep waters are largely anoxic, confining most life to upper layers, yet the lake sustains millions along its shores. Another remarkable water body is the Dead Sea, the lowest land elevation on Earth and hypersaline, where few organisms survive, and where human diversions are causing dramatic decline. Our ability to explore Earth's deepest points is entirely dependent on our technology. The primary workhorses of modern deep-sea exploration are remotely operated vehicles, or ROVs. These unmanned robotic submarines are connected to a surface ship by a tether that delivers power and two-way communication so operators can see and act in real time. Their arms can collect samples, rock, water, and even delicate deep-sea creatures. Another key tool is the Autonomous Underwater Vehicle, or AUV. Unlike ROVs, AUVs are not tethered. They are pre-programmed and explore on their own. They use sophisticated sonar to map the seafloor in wide swaths, creating high-resolution charts of underwater mountains, canyons, and trenches. After missions, they return to be recovered, and their vast data sets are downloaded and analyzed. Manned submersibles represent the pinnacle of deep-sea exploration, allowing humans to witness the abyss with their own eyes. These complex, expensive missions are reserved for key objectives. The first dive by Trieste in 1960 and James Cameron's solo dive in 2012 are legendary moments. Back on land, scientists analyze samples, study genetics, and examine water chemistry to understand the processes that fuel deep ecosystems. They analyze sediment cores, layered histories of the ocean's past, each sample adding a new sentence to the growing story of the deep. The deep places of our world, oceanic trenches and profound lakes, hold a sense of boundless wonder. They are a final frontier on our own planet, a realm of immense pressure, absolute darkness, and life that defies our expectations. These places teach us about the resilience and adaptability of life, showing that it can flourish in the most unlikely homes. They reveal the immense geological forces that shape our planet and hold clues to past climates. Our explorations must continue, but must proceed with care and respect. The deep sea is critical to the health of our planet. It regulates climate by absorbing heat and carbon dioxide. Its vast ecosystems are interconnected with the sunlit world in ways we're only beginning to understand. The threats are real: pollution, destructive fishing practices, deep-sea mining. We must act with wisdom, establishing protected areas and insisting on a precautionary, science-first approach. The choices we make now will determine the future of a world most of us will never see, but which is vital to us all. We will keep listening to the silence of the abyss, to learn about the world below and about our place within the interconnected web of life.